No problem. See you guys. No, I haven't touched it yet. I just finished those last night, and today I've been busy. But I'm gonna do it all. I'm doing it all tomorrow, so you have it by Wednesday.
Oh, you're gonna do it all tonight?
Not tonight, tomorrow.
Oh, I thought you said I'm gonna do it all tonight.
No, I finished grading those last night.
Okay, are we going over this again?
So I do want to go over because there's some additional things that, especially for 540 people, you haven't seen. And so the MATLAB stuff that I said is going to be at the end. So I want to talk and make sure that we're on the same page for that. And I want to talk about the requirements for each of the other ones. So we'll go over that just quickly for the first 5 minutes, and then we'll jump into some new theory for today.
Yeah, I'm not looking forward to the MATLAB.
Mhm.
I'll probably see you tomorrow morning to talk about that.
Okay. No problem. See you guys. Hey guys. Hey Aaron. It's good. I'm having a I think there's some technical issues with the Wi-Fi, and so it kind of disconnected my iPad earlier, so I hope it doesn't show up again. But besides that, my lower back is killing me right now. I don't know. I think I pulled it this morning or something because I'm having a hard time standing for long periods of time. So I was able to stand during my last class, but I might have to sit. I might have to sit today. Yeah. Oh, Aaron, I got your email. I'm happy to be part of your committee. I just haven't had a chance to respond, but I did want to tell you that, I'd be happy to be. Yeah. Yeah, I just have to look at my schedule and see when's kind of a good time, but but I did want to tell you that, I'd be happy to be. Oh, shit. I hope not. These are.
Graded it already?
No, I graded the. This is why I don't sit down. There we go. Okay.
By any chance, do you have access to lab rooms?
I do. You mean like these rooms here?
No, the E24 seat.
Oh, I have access to the wind tunnel lab, but I don't think I have access to the other rooms. All right, it's 7 o'clock, so let's go and get started. All right, so first of all, let me apologize because my lower back's been killing me today. I don't know if I pulled it last night, and so I'm going to be sitting down. And so if you have problems, if you have problems hearing me or anything, just let me know. But I'm going to try sitting down. Although ironically, it might make my back worse. But we'll see. It's at least less painful to sit here than it is to stand, which I did all of last lecture. But a good evening, everyone. How's everyone doing today? It's good. It's good. After the midterm, everyone's feeling good. So I haven't started grading your midterms yet. So I actually had three classes take midterms last week, and so I graded the first two. And unfortunately, you guys were the last ones because you guys were the last ones to take them. But I cleared my schedule tomorrow, and so my plan is to just knock them all out tomorrow. And so you should know your grade on Canvas sometime tomorrow, and then I'm going to give the exams back on Wednesday. Okay. Try laying down. If I didn't have to teach for the next hour and a half, then I would. But yeah, probably after this, I'm gonna go lay down in my office on the floor. Right, and so I because I'm going to be returning the midterms Wednesday, I would like everyone to come pick them up in person. And so when I grade exams like this, I do my best to try to leave as many comments as I can to give you feedback on kind of where I think you went wrong on certain problems. And so of course, you get the most from that by reading them yourself. And so, if you could come to class, on Wednesday, it doesn't have to be Wednesday too. I'm in my office most of the week. And so if you can come to campus sometime to pick it up, that would be great. But if you can't come to campus this week or next week, you can let me know. Then I can scan yours. I can scan your exam as well, just to make sure you have my feedback. But I don't want to do that for too many people because then it gets a little bit crazy to have to scan a couple of dozen exams. Question?
I was gonna say find it from next week.
Okay, yeah. Next week is fine too. Just as soon as you get them. And so after I grade the exams, I'm also going to post the solutions on Canvas as well. And so you can check your solutions. And so I don't try to, but I'm human too, so I make mistakes when I grade. And so when you get your exam pack, please check against the solutions just to make sure that I didn't make any mistakes, or I might have added your points up wrong. And so if you do, if that does happen, then please let me know as soon as you can, and I'm happy to look at it again or to correct any mistake that I made. Okay. Okay. And so I think that's the announcement. Oh, I did want to go over the ANSYS activity, just kind of very briefly, because I know we got cut off a little bit at the end of last class. And so I want to make sure that everyone's kind of on the same page for the requirements, especially for the MATLAB part. I want to make sure I talk about that, before we launch into the next thing. And so that's kind of my plan for today. Okay. And so before we jump in, are there any questions I can answer? Okay. All right. So let me go back to, and so you don't have to open up ANSYS again, but I just wanted to make sure that that we all are kind of we're all kind of on the same page with the requirements, because we kind of just talked about the ANSYS stuff last time, and we didn't really talk about what the requirements for the activity are. Yes. Okay. All right. So if you recall from last time, the subject for ANSYS activity 2 is to run a simulation on the following bike crank. Okay. And so last time we loaded it together in ANSYS, we defined a custom material property, we suppressed parts, we meshed it, and we left off on the boundary conditions. Okay. And so just like I told you last time, I want you guys to decide, where you think it's best to apply the boundary conditions. Okay. My only requirements are that you apply a fixed constraint somewhere. It's a lot hard to do when sitting down. Okay. And so there should be a fixed constraint or fixed support somewhere in your model. And there should be a single 100-pound force somewhere in your model as well. Okay. Okay. Where you apply these, I'll leave it up to you, but it should make physical sense, right? And so it shouldn't just be kind of a random application of these. Right? And so if you look at the geometry of the bike crank, remember what I said was that this portion of the bike crank here with the 3 holes, this is the part which attaches to the actual bike, okay? And this part right here is where the pedal used to be, okay? And so the situation that that I'm having you simulate is, a case where, let's say the bike kind of gets locked up, and so there's maybe something got caught in the chain, and so the bike crank kind of locks up, and someone applies a 100-pound force on the pedal, okay? And so I want you to simulate the case, or the worst case scenario of what would cause this bike crank to break, okay? And so I'll let you decide, where you want to apply that support and how you want to apply the force, but that's my only requirements, okay? Okay, so problem 3 here is predictions, and so this is a really important step for any finite element simulation that you do, or any simulation, is that you should have some kind of idea of what's going to happen to your simulation before you actually run it. Okay, because an issue that you're going to run into, now especially because because if this is your first time running ANSYS, then then things are bound to go wrong. But even if you've used ANSYS before, even if you're a veteran, you should have an idea of what your solution should look like before you actually run it. Okay, because that's how you're going to check your results. Because what's going to happen a lot of times is that you're going to have a situation like this, and you're going to expect it to behave a certain way. But when you run the simulation, maybe it doesn't line up, or maybe it doesn't, maybe the results aren't what you expect. Okay. And those are situations where you have to go back and say, like, did I set up the simulation properly? Are my predictions accurate, right? And so it's a really important debugging step for you to do. And so I really want you to kind of pay attention to problem 3 here. Okay. All right, problem 4 is to just look at the results. Okay, and so what I want you to do is I want you to output the field of the total deformation, normal stress, and the equivalent stress. Okay, so you should have at least 3 figures here. Okay. And if you read the text of this problem, it goes into a little bit of an explanation of the difference between normal and equivalent stress, right? And so that's useful. Okay. And there are some questions here that I want you to answer based on your results. Okay, so make sure you answer those. Problem 5 here is to find the maximum load. And so after you've applied the load in a certain way, what you'll see is that the bike crank shouldn't be failing, and so it shouldn't be breaking. Okay. And by breaking, what I mean is that the maximum stress, or the maximum equivalent stress that you observe in the part, it should not exceed the yield strength. Okay, and so the yield strength for this part is we're going to assume it to be 35,000 psi. Okay, and so what you should see is that from your initial simulation, and you apply a load of 100 pounds, the maximum equivalent stress should not exceed 35,000 psi. Okay. And so what I want you to do is I want you to take that same simulation and then increase the load until you reach the yield strength, okay? But I want you to do this with a factor of safety of 2.0, okay? And so what I mean by that is that I want you to push the bike crank not until it reaches 35,000 psi, but I want you to push it until it reaches 35,000 divided by 2, okay? And so that's 17,500 psi. Okay. Okay, and so you don't have to change the direction of the loading. All I want you to do is to increase the magnitude of the loading. Okay, and so I want you to go, let's say you start at 100 pounds. Okay, then you would change it to something like 110 pounds. Right. Right, and then you check and see what the equivalent stress is. If the equivalent stress is still less than 17,500, then you would increase it again. Okay, be 120 pounds. Okay, and then you check and see if it's exceeded. If not, you increase it. But if you did increase it, maybe you take it back to maybe like 117 pounds. Okay. Right, and so I want you to basically use ANSYS to iteratively solve for what's the maximum load that this bike crank can take. Okay. Okay. So does that make sense to everyone? Any questions on that? Okay. All right, so that's all the ANSYS parts. But if you looked at the bottom of the map of the ANSYS activity, there is some stuff I want you to do in MATLAB as well. Okay, because remember, right before we did the this ANSYS activity, we were working on our frame code, right? And so problem 6 here is to use that frame code to solve this problem. Okay. And so this problem here is a 1, 2, 3, 4, 5, 6 element frame. And so if you were to solve this by hand, it would probably take you the better part of, of the weekend, right? And so I think this was the very last part. I think this is problem 4B on the last homework. But I told you to, it was optional to do it by hand. And so what you're going to do now is solve this with code, okay? And so I don't want you, so I've already posted the solution to the frame code. And so if you go to our weekly view, we go to week 7, okay? You can download the solution to the frame code here, okay? And so of course, I want you to fill in the rest of the code that you didn't fill in the class and make sure that you understand all the parts here. But the whole idea with the frame code is to use this code to solve all different kinds of frame problems, okay? And so, the whole idea is that you could use this code and you don't modify anything below this line, okay? Let me do that better. Anything below this line right here, okay? Right, and so above this line, which of course doesn't kind of goes up with it, okay? And so above this line, you're gonna define things like the number of elements, the connectivity, the properties, and all that stuff, okay? And so the idea and kind of the motivation behind writing this frame code was that if you wanted to apply this code to a different problem, you would only have to modify the top portion of this code, okay? And so everything with the element stiffness matrices and the assembly, we wrote those in a very general way on purpose so that they can be applied to, lots of different problems, okay? And so when you apply this, and so when you go to solve, problem 6 on the ANSYS activity, you can use this code here, but you only have to modify just this top portion, okay? So actually everything here on the first page. And so the number of elements, the number of nodes, of course, you have to modify the connectivity, the properties, okay? So the Young's modulus, the cross-sectional area, the moment of inertia, and the length, okay? And as well as their rotation angles, and as well as the boundary condition information, okay? But everything past this, you should not have to modify, right? And so the idea is to write a general frame code that will tackle all different kinds of frame problems. The only caveat is that you have to update the code for the different frames that you're solving for. So you have to update the number of elements, the number of nodes, connectivity, and so on and so forth. Okay. And so problem 6 on the ANSYS activity, I don't want you to write any new code for that, right? You can use the code that I've given you already. You just have to update, the properties and the boundary conditions to reflect that frame problem. Okay. And so the reason I'm assigning that as a problem is I want you to understand how this frame code works. Okay. And the best way to understand how it works is to actually use it for a problem. Okay. Because I think last time we talked a lot about the implementation, but actually using it in practice is also an important skill, because we're going to be writing codes like this and implementing codes and using codes like this, in different parts of the class as well. And so it's important that you understand kind of how it works and what the different sections of the code mean. Okay. And so problem 6 is just going to be just to use the code that I provided for you. Okay. Problem 7, I actually want you to implement a new code. Okay. And so what you're going to do is you're going to take the shell or take the skeleton of the frame code that I've already provided to you, and then modify it to work with the 2D truss. Okay. Actually, I think I do have a starter code for this as well. I need to upload it onto Canvas, and so I have a starter code, but the starter code is basically just going to be the same frame code, just gutted, to make room for the truss stuff. Okay. And so I know this is going to be, I think this is probably going to be the most challenging part of this activity, because it's going to involve you kind of implementing MATLAB code on yourself. Okay. And so you're going to use all the same theory that we went over when we were implementing the frame code from scratch. It's just that you're going to modify the steps to make it work for a 2D truss instead. Okay. And I did this on purpose because the 2D truss is not as complicated as a frame. Okay. So the element stiffness matrices are smaller, and generally it's a bit easier to compute. So I wanted to make sure we do the really hard one together, so that you do kind of the slightly easier one yourself. Okay? And I've broken it down here. And so if you look at parts A through F, and if you read those steps, I've kind of broken it down into each of the individual tasks that you need to do, all the individual changes that you need to do in order to implement this code. Okay. And so if you follow this problem, steps A through F, you do them one at a time, then you're going to finish the implementation. But what I thought I'd do is I'd break it down into steps for you, just so that you can see, what steps that you need to do to accomplish this code. Okay. But with that said, I realize that this part's still going to be really difficult for a lot of people, especially depending on how you feel about MATLAB. And so definitely reach out if you're having trouble with this, because it is going to be a challenging part. And because we didn't talk about that, I know here I said the due date is this Friday. That's not going to be due this Friday, so it'll be due next Friday. Okay, because I want to make sure I give you guys time to work on the MATLAB part. So it's going to be due Friday, March 25th. Okay, and so actually let me update that on Canvas right now so that you can see, because I'm probably going to forget later too. Okay. Okay, and so are there any questions on this activity here? It's going to be due 25th. Okay. And so the MATLAB part's going to be challenging, and so make sure you start on that, sooner rather than later. Okay. And so I'll post a starter code for tonight, if I do have one. I think I have one, but I need to go and check. If I don't have one, I can make one really quick. Okay. And so you can use that starter code to help you out with the last problem. Okay. All right. So let's go ahead and bring it back to the iPad. Hopefully the iPad doesn't spaz out, because it was definitely doing that earlier. All right, and so now let's go ahead and start the next portion of the class, which is on general finite elements. Okay. And so I call this unit general finite elements, but that's not really its name in practice. And so if you ask anyone outside of this class about finite elements, they won't call it general finite elements. They'll call it this is just finite elements. And so, I would say the majority of the community, when you say finite elements, without any modifier, this is kind of the theory that they're thinking about. Okay. And so the stuff we've been doing before this with the stiffness method, the reason I go over it is it's not like that was fake finite elements or anything. That's real finite elements, but it's kind of in a very derived kind of niche form that kind of takes away a lot of the math. But the reason I do that is I want to kind of highlight to you guys what the finite element process is, and that process involves discretizing your domain, forming the element stiffness matrices, assembly, boundary conditions, solve. Okay. So that process is the same no matter what. It's just that the direct stiffness method kind of simplified some of the steps in the middle so that we could focus on the process. Okay. And the main step that's going to change, now that we're on general finite elements, is going to be the element stiffness matrices. Okay? And so in reality, with the direct stiffness method, I gave you these kind of really nice packaged, formulas for the element stiffness matrix for a truss and a beam, for a frame, right? And so those are kind of pre-packaged matrices that we can just plug and chug, basically. In reality, the computation of the element stiffness matrices kind of constitutes the bulk of the work, and that's what kind of, that's the part that's kind of mathematically challenging for a lot of finite elements. Okay. And so that's usually the most difficult part of the finite element process, is to, how do we compute these element stiffness matrices? Okay? And as we get into the theory, you'll start to kind of understand why, why that's the case. But the, okay, go ahead and enter the door, close it. Okay, fuck it. I'm gonna stand. It hurts to sit down too. Okay. And so once we kind of get into theory, you'll kind of understand why this is. But hopefully you kind of appreciate kind of why we started with the direct snippets. Because as we kind of get through the math, it's gonna be really easy to kind of lose your way. And what I mean by that, there's a lot of devil in the details here. And so throughout all that, I don't want you to kind of forget what the finite element process is. It's just that, we're going to be hyper-focused on just one specific step, okay? And that's the element stiffness matrices, okay? But all the other steps are going to be the same. Okay. And so I want you to always kind of remember that over the next few weeks as we go through this theory, okay? All right. And so the main reason why the element stiffness matrices are going to be a lot more challenging here is that the way we're going to compute them is going to be based off a differential equation, okay? We're going to start with ordinary differential equations, so we're going to start with ODEs, but then we can also extend this to PDEs as well. Okay, and actually, if you ask anyone, what finite elements is, what they'll tell you is that finite elements, actually doesn't have anything to do with structures or heat transfer or fluids or any of that. Okay, finite elements is just a general methodology for solving differential equations. Okay. Specifically, people are referring to PDEs when they say it's a method for solving differential equations, but you can solve for ODEs as well. Okay. All right, question. So is the term stiffness matrix used for thermal and fluid FEA as well? It is actually, yes. And so the community kind of adopted the terminology stiffness matrix because some of the first problems that FEA was used to solve was actually structural problems. And so stiffness matrix kind of made sense for those. But as people started to use the same methodology for thermal and fluids problems, because those are governed by differential equations as well, the name kind of stuck. And so that's why we're kind of stuck with the same stiffness matrix, even though you can actually use it for almost anything. If it's governed by differential equation, you can use FEA to solve it. Okay. Okay. And so that's where our big shift is going to be. So we're going to focus less on kind of specific structural elements, and we're going to focus instead on kind of just general differential equations. Okay. Okay. And so to do that, we're going to need some new terminology. Okay. And so the first term I want to go over is something called the boundary value problem. And so a boundary value problem is basically it could be a physical problem, it could be most times a mathematical problem, which has the following characteristics. Okay. Okay. One, the first thing it has is it has a defined domain. Okay. Okay. And the defined domain also has defined boundaries. Okay. So it has to be a finite domain, and so we can't be solving this for to infinity and beyond. Okay. Right. So number two is we have to have some kind of differential equation And that differential equation is there to define the physics of the problem. Okay. And number three is we have to have boundary conditions. And the purpose of the boundary conditions basically defines how the solution behaves at the boundaries of our domain. Okay. All right. And so I'll give you kind of the abstract kind of mathematical form of this. Okay. And so, first thing that we need is we need some kind of boundary. Okay. And so here I've drawn, I attempted to draw a potato, but it looks like kind of a smooth piece of toast. Okay. All right. And so the mathematical symbol that we usually give the domain is omega. Okay. And specifically, omega refers to the interior of the domain. Okay. Whereas the boundary we give it the symbol partial omega. Okay. Right. And so when I refer to partial omega, I refer to something that's on the boundary of our domain. Okay. Next, we have some kind of differential equation. Okay. And this differential equation tells us how our solution is going to behave on the interior of the domain. Actually, let me change these symbols just because I know someone's going to ask. Okay. Let's say that this is the heat equation. Okay, so that's kind of simple heat equation there. Okay. And so here is our differential equation. Okay. And then we also have some kind of boundary condition. Okay. And so the boundary condition, since we're going to be solving for temperature here, okay, we have to define what the temperature is going to look like on the boundaries of our domain. Okay. Yep.
So the differential equation tells you how your interior domain is?
Exactly. Yes. And so it basically says, from point to point in the interior of the domain, how is the solution going to act between those points? Yeah. Okay. And this right here is a boundary condition. Okay. Of course, in reality, your boundary conditions are going to look a lot more complex than this, but you have to have at least one in order to solve the problem. Okay. All right. And so if you solve this boundary value problem, okay, and here I just have one in 2D, and so we just have x and y directions, and so our solution in this case is going to be a function of x and y. Okay, and so in particular, it's going to be our solution t as a function of x and y. Okay. All right. Looks like the Wi-Fi is doing better, so that's good. Okay. All right, so this is kind of the most general kind of definition of a boundary value problem, and you can apply this definition of boundary value problems to a lot of problems. And so if you think of and so I know I'm showing the heat transfer equation here, the heat equation, but you can apply the same definition of boundary value problem to any kind of structural problem as well. Okay. And so technically speaking, all the direct stiffness problems that we've been looking at, they fall under this category as well, right? And so you have a defined domain with defined boundaries. You have boundary conditions on that. Those are loads and supports. The only difference is that the differential equations that define the middle of the domain, we didn't really talk about them too much. We kind of just talked about kind of the results of those. Okay, and so that's why for this portion of the class, we're going to be focusing on this. Okay. basically, how do we go from a differential equation, which is just a kind of a mathematical construct like this, how do we go from something like that to an element stiffness matrix? Okay, and so that's going to be the focus of this week and next week up until the break. Okay. Any questions on this? Okay. All right. And so the next thing that we're going to cover is the different forms of the differential equation that we can have. Okay. And so the next part is titled strong and weak forms. Okay. And so the strong and weak forms, these refer to different formulations or different ways to express the governing differential equation. Okay. Okay. But I want to say something kind of straight up because, I will say that whoever picked the terminology for this was really dumb, because whenever you see strong versus weak form, you naturally think the strong form is better, right? That's the natural thing to do. But what I want to tell you is that there's no difference in the goodness of these two forms. Okay, so they both are the same problem. They're just expressed in different ways. But the weak form is not inferior to the strong form in any way. Okay? And so if you solve both forms, you get the exact same thing because it's the same problem. It's just that mathematically they have different expressions that work well for different forms. Okay. Okay. So both are valid. They just they just have kind of these strange names. Okay. And so the reason I'm bringing this up is that normally when you think of a boundary value problem, I think probably that you've experienced in other classes. So I know probably everyone's taken 438, 538, right? And so when you look at a differential equation, most of the time they're expressed in the strong form. Okay. And that's great. That's the form that you basically see a lot of these equations in. Okay. Just because just logistically it's a lot faster to write the strong form. But the reason I bring up the weak form is that the finite element method is actually based off the weak form. Okay. And so the first thing we're going to do is we're going to learn, what the strong form of a boundary value problem looks like. Then we're going to learn how to convert it to a weak form. And then next week, we're going to take that weak form and actually turn it into a finite element problem. And so it's kind of a 2-week, this is kind of a 2-week kind of thing that goes together. Okay. Okay. And so let's start with an equation that is closely related to what we've been doing, where we're going to look at the mathematical form. Okay. And so we're going to look at the 1D elasticity problem. Okay. And we're going to look at its strong form. Okay, so let me go ahead and draw a picture for you. Okay, so let's say that we have a situation like this. So we have a truss element here. Okay. On one side of the truss, we're going to have a load. Okay, and this load is going to be expressed as an applied stress. Okay, and so we have T bar, and so T bar here is an applied stress. Okay. This rod here has a length L. Of course, on this side, because it's attached to a wall, this side is fixed. Okay. And then I'm going to introduce something that we haven't seen before, which is a body force. Okay. We'll model that as B of X. Okay. And so a body force is something like gravity. And so it's basically a load that's applied throughout the entire body. Okay. And so it's a little bit strange to see it here in the horizontal form because there's not that many body forces that actually act horizontally. The only one I can really think of is electromagnetism. But usually body forces are meant to simulate like gravity or something like that. Okay. Or you can even use it to simulate like some kind of distributed loading as well. Okay. And so for 1D elasticity, we have a structural member like this, and it's under some kind of load. And so the goal is that we want to compute the spatial distribution of displacement along our member. Okay. And so displacement is going to be our primary solution variable. So that's what we're going to be solving for first. Okay. And so in other words, we're going to get a function u of x. That's the goal. Okay. And a few other properties that we're going to need. We're going to need the Young's modulus. Okay. And we're going to need the cross-sectional area. Okay. But instead of assuming that they're constants, what we're going to have here is we can assume that the Young's modulus and the cross-sectional area can also vary with x. Okay. Okay. All right, and so that's our situation. Okay. And so next we're going to go over the how we can express this mathematically, and then we'll go over some more details on that. But any questions on this so far? Okay. Okay, and so the strong form of the equations looks like this. Okay. And so what we have is we have d dx, okay? And so that's the derivative with respect to x of the quantity e of x times a of x du dx, okay, plus b of x is equal to 0. Okay. Right, and so what you can see here is that we have this is a differential equation. Okay, it's an ordinary differential equation because we only have one independent variable that we can solve for the displacement in the row. Okay. Okay. And so for the case, let's take a usual case. And so let's say that we have a constant Young's modulus and we have a constant area. And so if these two are constant, then we can pull them out of the expression. Okay. And then we can just apply a double derivative to u of x. Okay. And then we can just if we know b of x, then we can just simply integrate this equation to solve for u. Okay. All right. So I'll do an example of that later, but I do want to talk about the mathematical form of the boundary condition before we get there. Okay. And so the term boundary conditions, remember, we've always defined them as defining our solution behaviors at the extremities of our domain. Okay. And so for a 1D problem like this, we only have two boundaries. Okay. And so we have the boundary at the left side of the domain, and we have the boundary on the right side of the domain. Okay. And so our first boundary here is going to be at x is equal to 0. And our other boundary is going to be at x is equal to L. Okay. And so, I'm going to define the boundary conditions for this specific problem up here, but just know that, and for this problem, we have an applied stress on the left and a fixed boundary condition on the right, but that can change, right? And so, you have to kind of pay attention to the problem to see where the boundary conditions are applied. Okay? And so at x equal to 0 here, we have an applied stress, right? Okay. And the applied stress has a magnitude of t bar. And what we can do is we can use a stress strain equation to turn this into a boundary condition. Okay. Okay. And I should have left more room, so I'm going to erase this for a second. I apologize. Okay. And so remember, our stress strain equation is E times epsilon is equal to sigma, right? So this is our usual Hooke's law. Okay. Epsilon here we can substitute, because we have a function of the displacement. One way that we can express the strain is simply take the derivative of the solution. Okay. And our sigma here, this is our applied stress. Okay. And if we're going to plug it into this equation, because this equation here, is has the strain involved, the stress that we're going to plug in is actually going to be a minus t bar. Okay, where the minus here is to indicate the fact that this stress is compressive. And so you have to be careful applying these kind of stress boundary conditions, because it doesn't really follow the traditional XY directions. What they follow instead is either compressive or tensile. Okay. And so for the boundary condition on the left, what we have is E multiplied by du dx. Okay. And we evaluate this entire quantity at x is equal to 0. Okay. This can be equal to minus t bar. And so that's going to be our boundary condition on the left. Okay. And I'm going to relate this to a term that we've seen before. Okay. And so since this is essentially a load type boundary condition, right? So we're essentially applying a force on the left-hand side. This is classified as a Neumann type boundary condition. And so any boundary condition that you have on that's a load, we define that as Neumann. Okay, but because of that, we can come up with a more precise definition of Neumann boundary condition. Okay, and that more precise definition has to do with this. Okay. Notice how in this boundary condition, we have a specification not on the function u, but instead on the derivative of u. Okay. And so this is common with all Neumann type boundary conditions. So another definition for Neumann type boundary conditions is that they involve specifications on the solution derivative. Okay. Okay. And so any boundary condition where you're specifying the derivative of the solution, that's classified as a Neumann type. Okay. Right. And so up to this point, we've been calling our low type boundary conditions Neumanns because they always involve the derivative of the solution at some point. Okay. Because they always involve the strain in some way. Okay. Any questions on this? Okay. So let's talk about the boundary condition on the other side. Okay. And so at x equal to L, what we have is a fixed support. Right? And fixed supports, we know that the displacement here is going to be 0. Okay. And so mathematically, this has a very simple form. Okay. And so at x equal to L, okay, what we can say is that the displacement u is equal to 0. And we know from before that when we apply these fixed supports, these are called Dirichlet type boundary conditions. Okay. And so because of that, we can come up with a slightly more specific definition for Dirichlet. Okay. And so Dirichlet type boundary conditions specify the value of the solution itself at the boundary. Okay. And so those are two, more mathematical definitions of our two types of boundary conditions, right? So one specifies the derivative of the solution, the other specifies the value of the solution itself. Okay, Neumann Dirichlet. Okay. And so through that, now that we have we already have the domain, we have the differential equation, and now that we have the boundary conditions, we can fully express the full boundary value problem for this example. Okay. And again, this is in the strong form. Okay. And so the strong form of this equation is going to be d dx of e times a du dx, okay, plus b of x is equal to 0. Okay. And so this part here, or this differential equation, defines the solution between the values of x and of 0 and L. Okay. And so the way we express that mathematically is we say that this differential equation is valid between 0 is less than x, which is less than L. Okay. I use the less than signs very deliberately. So I didn't say less than or equal to, because when x is equal to 0 and x is equal to L, we don't have this equation anymore, but what we have is our boundary conditions. Okay. And so our two boundary conditions are this. And so we have E du dx applied at x equal to 0. This is equal to minus t. Okay. And this is valid at x is equal to 0. Okay. And our other boundary condition is u is equal to 0. And this is valid at x equal to L. Okay. And these are our boundary conditions. Okay. And so, if you remember, if you go back to our definition of boundary value problem, you can see that all the components are here, right? And so first of all, we have our domain. Okay. And it's not a pretty picture of the domain, but we have the mathematical form. Okay. And so this here you can see is our domain. Okay. And this right here are our domain boundaries. Okay. Next, we have our governing differential equation. Okay. And then, of course, we have our boundary conditions, which I've already labeled. Okay. And so all the components of our boundary value problem are here. All right, so I did want to do an example just to kind of show you, how to solve these for a simple case. Okay, and then from there we'll move on to the weak form. But any questions on this before we jump over there? Okay, all right. So let's go ahead and do a very simple example just to kind of show you, how we can solve these. Okay. And so let's consider a simple truss bar in tension. Okay. Okay. And so there we have a truss bar, and we're going to pull on this truss bar with a stress of 100 pascals. Okay. We're going to assume that the Young's modulus is constant at 100 kilopascal. And we're going to assume that the area is also constant at 0.1 meters squared. Okay. And so both of those are constant. So we don't have to integrate those. Okay. And then we're going to compute the displacement distribution U of x. Okay. Okay. And so let's start with the differential equation for this guy. Okay. And so our differential equation is d dx of EA du dx plus b of x is equal to 0. Okay. All right. And so another thing that you should see is that we don't have any body force here, and so the b of x is going to be 0. Okay. And since E and A are constants, we can just pull them out of the derivative here. Okay. Okay. And so the reason we have them inside the derivative at first is because we're planning for the possibility where E and A can depend on x. But in this case, E and A don't depend on x, and so we can just pull them out. Okay. And so we have E times A times d squared u dx squared is equal to 0. Okay. And in fact, because E and A are constants, and more importantly, they're non-zeros, we can divide both sides by E and A. Okay. And that's going to get rid of that. And so our ending differential equation is d squared u dx squared is equal to 0. Okay. All right. And so from here, we're interested in solving for u of x. And so from here, all we have to do is just integrate. Okay. And so we're going to take the integral both sides. Okay. We're going to take the integral with respect to x, and so we're going to put dx on both sides. Okay. And so on the left-hand side, our integral is going to cancel 1 power of the derivative, and so we're going to have du dx on one side. Okay. On the right-hand side, we have integral of 0. Integral of 0 is just 0. But because we're doing indefinite integrals here, and so we don't have any bounds, we have to add a constant. Okay. And so this integral, if you want to be more technical, this integral, or the evaluation of this integral, right? So we're integrating 0, and so the integral of 0 is just 0. And then to that, we add an arbitrary constant C1. Okay. All right. And so that's one integral down. And so next thing we're going to do is we're going to integrate one more time. Okay. And so we integrate one more time with respect to x. What we get on the left-hand side is we get u of x. Okay. And on the right-hand side, we have integral of c1. And so integral of c1 is c1 times x. Okay. And again, since we're doing an indefinite integral, we have to add an arbitrary constant c2. Right, and so here is our general solution. So fairly straightforward. And so we just performed an integral, and that gave us a couple integrals, and that gave us our solution. Any questions on this part here? Okay. All right, and so to solve for the constants C1 and C2, what we have to do is we have to apply boundary conditions. Okay. And so let's look back at our original problem statement and see what our boundary conditions are. Okay. Okay. And so actually, let me go ahead and define these parts of the domain. So we'll say this is x equals 0 and x equal to L. Okay. Okay, so first thing we have is we have a boundary condition at x is equal to 0. And so we can see there that we have a pin support. And so when we have a pin support, we know that the displacement there is going to be 0. Okay. And so we have u of 0 is equal to 0. Okay. And so on the left-hand side, we have a Dirichlet boundary condition. While on the right-hand side, we have a stress. Okay. And so the right-hand side, we're going to have a Neumann type boundary condition. Okay, so let's go ahead and implement that as it is. So let's start with the Dirichlet boundary condition at x is equal to 0. Okay. And so we have u of 0. Okay. We know that displacement there has to equal 0. And so let's plug in for x into our general solution. Okay. So we have c1 times x, but instead of x, we're going to plug in 0. Okay. And then to that, we're going to add c2. All right, and so we have c1 times 0, and so that, of course, is going to cancel out. And then all we're left with here is that c2 is equal to 0. Okay. And so if we plug in c2 is equal to 0, then what we have is u of x is equal to c1 times x. Okay. Okay. All right, and so the other boundary condition we have is a Neumann type boundary condition at x equal to L. Okay. Remember, the way that we define Neumann type boundary conditions here for elasticity is we have E times du dx. Okay. And we're going to evaluate this at x is equal to L. Okay. This is going to equal to T bar. We have a positive T bar here because it's a tensile force. Okay. And so from the problem statement, we know that the stress value there is 100. Okay. Okay. And so let's go ahead and plug in for this side of the equation. Okay. So first we have E, and so E we know is 100 kilopascal. And so if we convert that to Pascal, this can be 100,000 Pascal. Okay. Then we have du dx. And so du dx, so we take the derivative of this quantity here, we just end up with C1. Okay. Okay. And all that's equal to 100 Pascal. So if we perform the division, we get C1 is equal to 100 divided by 100,000. Okay. And so C1 is equal to 0.001. Right. And so we plug that back into our general solution. What we get is u of x is equal to 0.001 x. So hopefully that example was a trip down memory lane. And so, I bring up this example, not because it's difficult, right? So that problem was fairly straightforward. But just to show you that, these strong form equations, these are kind of differential equations that you've seen before, right? And so you have methods for solving these, from before, okay? And so I wanted to kind of jog your memory of that and to kind of drill home this definition of strong form, which is basically just differential equations as you've seen. Because what we're going to do next is we're going to introduce the weak form, and you'll see the exact same problem, but just phrased in a different way, okay? But I want you to remember, kind of where we're coming from. Okay, so any questions on any of this? Okay, all right, so let's talk about the weak form now. All right. And so the starting point for any weak form is actually the strong form. Okay? And so we're going to start with the strong form of the equation, and then what we're going to do is we're going to basically manipulate this or massage it into a different form. Okay? All right, so let me go ahead and write down the strong form for this. Okay? Okay. All right, so there's our strong form of the equation. Okay. Same as it was up there. Okay. But I want you to notice something about this equation right here. Okay. Actually, we'll go over in a bit. Okay. And so the first thing that we're going to do is we're going to do something very strange. Is that we're going to take this entire equation and then multiply it by another function. Okay. And we'll call that function w of x. Okay. And what is this w of x, you ask? Unfortunately, it's a little bit too early to kind of talk about what this function is, but you can think of it as an arbitrary function. Okay. And so arbitrary really means arbitrary. So at this point, it can be anything. Okay. And so of course, I know that begs a lot of questions. So how could it be anything, right? But just kind of trust me at this point. It can really be anything. Okay. Even though it can be anything, we do have to place a requirement on this, okay? On this function. Okay. And that requirement is that wherever we have a Dirichlet boundary condition on U, then W must disappear at those boundaries. Okay. Okay. Right. So basically, whenever we have a Dirichlet boundary condition on U, then W has to have has to disappear at those places. Okay. Okay. And so we've introduced this function W. Okay. Very strange, I know, but we're going to do another strange step after this. Okay. And so now that we have this, now that we have our strong form multiplied by this arbitrary function, what we're going to do is we're going to take that entire expression there and integrate it over the domain. Okay. Okay. And so this entire expression here becomes integral. Okay. And we're just in 1D. And so we're going to integrate from 0 to L of W of x times ddx of EA du dx plus b of x dx, okay? And this is all equal to 0. Okay. What I'm going to do here is I'm going to separate this out into two integrals. And so you can see here that we have a plus, right? And so whenever we have a plus inside an integral, we know that we can always break it up into two, okay? And so from this, we have integral from 0 to L of w of x ddx of EA du dx, okay, dx plus integral from 0 to L w of x b of x dx is equal to 0. Okay. Okay. So strange steps so far, but kind of just, stay with me. Okay. All right. And so the next step that we're going to do is, this second integral is actually fine. You can kind of leave that as it is. We're actually going to work on this first integral right here. Okay. Okay. And what I want to highlight is that, oops, that's not what I wanted to do. I didn't want to erase. Okay. And so if you notice, right, if we take this w of x as kind of its own thing, okay, and then we consider this kind of group of functions here as kind of another term, okay, what you should notice is that the second term here effectively has two derivatives on u. Okay. Right. And so let's ignore e and a for a second, right? And so inside the derivative there, we have du dx. And so if we apply that d dx onto that du dx, then we essentially have a second order derivative on u, right? So we have d squared u dx squared. Okay. Okay. Meanwhile, poor w of x there has no derivatives, right? And so, if we look at kind of the balance between u and w, this is not fair, right? And so w, and so this part of the class always makes me laugh because it's like, we have the strong form of the equation and it was doing just fine. And then this w of x dude just invites himself to the party and then he wants to take some derivatives, right? It's like, who the hell are you, man? How can you, who invited you here? But that's kind of how it is, right? And so what we're going to do is we're going to take this expression, we're going to apply integration by parts. Okay. And the goal of applying integration by parts is to balance the derivatives between u and w. Okay. And even though this might seem like a really silly kind of esoteric step, it has a very big advantage that we're going to leverage later. Okay. Because after you do that, and so instead of having, a second order derivative there, after we apply this integration by parts, we're going to have two terms that have first order derivatives. Okay. And that's actually really, really key. And that's a key part to making the finite element method work. Okay. And so a big part of the finite element method, a big reason why it works is the ability to kind of take these derivatives and kind of break them down or separate them into different terms. Okay. Okay, so let's go ahead and take the integration by parts. And so in case you forgot how to do that, we have a function u, okay, and then we're going to take its derivative. And so we're going to take one part of the integral here and apply that there. Okay. We also have one part of the integral that we're going to define as dv, and then we're going to integrate it to find v. Okay. Okay, and so for the u part, we're going to have that be w of x. Okay, and so when we take the derivative of w, we're going to have dw dx. Okay, and then for dv, we're going to have everything that's the second term. So we have d dx of ea du dx. Okay, and so we take the integral of that, we have ea du dx. Okay, right. And so for integration by parts, we just take the different parts of the integral, we assign them to either u or dv, and then we do the opposite operations. Okay. Okay, and so from here, what we're going to do is we're going to go across here. Okay, so we're going to go diagonally down. I'll use a different color just to make it more clear. Okay. Okay. And so we're going to take u times v and add those together. Okay. Or u times v and multiply with the positive sign out in front. Okay. Then we're going to subtract du times v. Okay. We're going to subtract the integral of that. Okay. And so that's how we apply the integration by parts. Right? And so if we apply that integration by parts, this integral up here becomes w times ea du dx. Okay. There's no integral on that. Okay. But we are going to evaluate it at the integration bounds. Okay. So because the integral here was evaluated between 0 and L, it's almost like we've integrated this part. And so we're gonna basically evaluate this part right here, one time at x is equal to L, the other time at x is equal to 0. Okay. And then from that, we're going to subtract du times v. And so we're going to subtract integral from 0 to L of ew dx times ea times du dx dx. Okay. And then we can't forget our body force term. So we have integral from 0 to L, w of x, b of x, dx. Okay. And all this is equal to 0. Okay. And so we're almost done. Okay. And so the thing that I want to evaluate, before we kind of box this, is I want to evaluate these terms. Okay. And if you notice these terms, right, we're only going to be evaluating these on the boundary, right? Because we've kind of evaluated this integral. We evaluate this terms at x is equal to L and x equal to 0. Okay. And it's no coincidence that that x equal to L and x equal to 0 are our boundaries. Okay. Okay. And so we have w times ea du dx. Okay. Evaluated at x is equal to L. Okay. Minus w times ea du dx at x equal to 0. Okay. Plus all this stuff that I'm not going to write because of time constraints. Okay. Okay. All right. And so let's say, let's kind of apply this to a specific problem now. Let's say that we apply this to a problem. Okay. We apply this to a problem where we have a Dirichlet boundary condition at x is equal to L. Okay. We have a Dirichlet boundary condition there, as well as a Neumann boundary condition at x is equal to 0. Okay. And so in other words, our boundary conditions are the following. And so we have u of 0, or excuse me, u of L is equal to 0, as well as e du dx at x is equal to 0 is equal to t bar. Okay. And in fact, let's make it a compressive force. So let's make it a minus t bar. Okay. And so if you remember our requirement on our arbitrary function w, what we said is that whenever we have a Dirichlet type boundary condition, then our w function has to equal 0 there as well. Okay. And so that means w of L is equal to 0. And so that means this entire term right here goes to 0. Okay. Since w of L is equal to 0. I know we're out of time, but just give me one more minute. Okay? And so the other term that we can apply here is we can say that this e times du dx is going to be equal to minus t bar. Okay? And so if we put this all together, we end up with the following. We end up with the following function. Okay? And this following function is going to be the weak form of our boundary value problem. Okay, and so first we have our boundary term, and so our boundary term is w of 0 times t bar times a at 0, okay, minus integral from 0 to L dw dx ea du dx dx, okay, plus integral from 0 to L b of x w of x dx is equal to 0. And then this entire thing right here is the weak form of our 1D elasticity. And so you can see here we have a lot more integrals here than our strong form. But one nice thing about this expression here is that our Neumann type boundary conditions, they're baked directly into our equation. So we don't have to have any extra equations because of that. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. And so next time, we'll start out with this. We'll kind of expand on this a bit more. We'll talk about W a bit more and see what that is. And we'll talk about how we can actually solve these kinds of problems. Okay. And so thank you guys for staying a couple minutes extra. I apologize for going over. I hope you guys have a good evening, and I'll see you on Wednesday. Thanks, guys. Yeah, I need to do some stretches and lie down and stuff. Thanks, Catherine.
Yeah. But the other stuff I got around. Oh, yeah. So she said,
All right, Michael, any final questions before I close the Zoom? Okay, all right, so I'm going to close the Zoom. I'll see you on Wednesday. See you guys.